Now we continue to talk about optimization for multivariable functions, finding extreme values, meaning max and min. So previously, we talked about how to find local extrema. And then previously, we talked about how to find global extrema specifically on a boundary or a constraint curve. And now we come to the last part of this. We put it all together in order to find global extrema on a region. To help us understand this technique, let's remember what we know from single variable calculus. So for y equals f of x, if you want to find the global max and min, you find the critical points, and then you find the boundary values, which back then we called the endpoints. We plug them into f, and then comparing that handful of values, we find the highest and the lowest, and that's the absolute and that's the global max and global min. So now for z equals f of xy, we do the same thing. There's a mathematical theorem that says that the global max and min of a function on a closed domain each occur either at a critical point or a boundary point. So that's why we continue to use the same idea. Now, note that the first derivative test identifies local critical points, and as we previously saw, and that the Lagrange multiplier technique helps us find boundary critical points. So these are our candidates for global extreme values, and then we will just compare their function values. So as a side note, when we talk about boundary, note that for y equals f of x, the boundary is just the endpoint, it's 2 points. For a surface z equals f of xy, the boundary is a curve. That curve has infinitely many points. So fortunately, thanks to the Lagrange multiplier technique, we only need to test a couple of the boundary points, what we call the boundary critical points, and not actually all of them. Okay, so let's do an example in order to see how this all comes together using all of our techniques. Okay, so here we go. So let's find the global max and min for the function z equals x squared plus y cubed on the disk of radius 1 centered at the origin. So just as a reminder, circle means just the circumference, disk means filled in, it's the whole region. So let's take a look. So notice that we need to find the local critical points and we need to find the boundary critical points. So first, local critical points. So to find that, first derivative test, df dx equals 2x, and that's got to be equal to 0. And then df dy, which equals 3y squared, that's got to be equal to 0. This is very easy to solve. 2x equals 0. Solving that just gives us x equals 0. And then 3y squared equals 0. Solving that also gives us y equals 0. Therefore, we found local critical points. There's only one, and it's at 0, 0. Okay. Next, we must find the boundary critical points. So first of all, what is the boundary? So the boundary is our circle. And the formula for the circle is radius 1 centered at the origin, x squared plus y squared equals 1. So now we have to go ahead and find the boundary critical points. So to do that, we're going to need the gradient of g, and that equals 2x and 2y. And now we use our Lagrange technique. So using Lagrange multipliers, we know that we get the first equation, 2x equals some constant times 2x. Second equation, 3y squared equals some constant times 2y. And of course, we also have our boundary equation, which was x squared plus y squared equals 1. Okay, so let's go ahead and solve these two equations. So from the first equation, we get that 0 equals 2cx minus 2x, and then we can factor that. So 0 equals 2x times c minus 1. So solving that, we know that either x equals 0 or c equals 1. So this is going to give us a couple possibilities. So the algebra is slightly more complicated, but still we can do it. Okay, solving the second equation. We get 0 equals 2cy minus 3y squared. So again, factoring, we get y times 2c minus 3y equals 0. So solving that, we know that y equals 0. Or, this one's a little more complicated, 2c equals 3y, meaning c equals 3y over 2. Okay, so notice that the first equation gives us two possibilities. The second equation gives us two possibilities. So every pairing gives us four possibilities. So we've got four cases. So let's try out each of those cases. So case A, first condition x equals 0, or from the first equation we take the first condition, and then from the second equation we also take the first condition, x equals 0, y equals 0. Well, if that's the case, that just gives us 0, 0. Okay. Case B, we take x equals 0, and then we take c equals 3/2 y. So now we solve this out by using our third equation, which was the boundary equation. So this gives us 0 squared plus y squared equals 1. So that tells us that y equals plus or minus 1. That gives us two critical points. So we already had that x equals 0, and then y could be 1, or x is 0, and y is negative 1. Next, third case, we have c equals 1, and then y equals 0. So plugging that into the boundary equation, we get x squared plus 0 squared equals 1. So clearly solving, we easily get x equals plus minus 1, and that gives us two critical points. When we get x equals 1 with y 0, and x equals negative 1 with y 0. And then finally, last case, case D. C equals 1, and c equals 3/2 y. Well, given that, we can now solve for y, because we know that 1 equals 3/2 y, so we get y equals 2/3. And once again, plug it into the boundary equation. X squared plus 2/3 squared equals 1. That gives us x squared equals, well, that'll be 5/9. So therefore x equals plus or minus, taking the square root, we'll get rad 5 over the square root of 9, which is just 3. Oh, so what critical points does that give us? That gives us x is positive rad 5 over 3, while y is 2/3, and x is negative rad 5 over 3, while y is 2/3. Okay. So notice that checking the boundary, we get a whole bunch of new possibilities for the critical points. So our local critical point was 0, 0, and then we got 1, 2, 3, 4, 5, 6 new boundary critical points. So those are all the critical points, and we're going to need to plug them into our original function. So let's see what we got. So for 0, 0, plugging that into the function, remember our original function right here, z equals x squared plus y cubed. So plugging in 0, 0, we just get 0. Plugging in 0, 1, we just get 1. Plugging in 0, negative 1 to the function, we get negative 1. Plugging in negative 1, 0, we get 1. Plugging in 1, 0, we get 1. Make a little space there. Okay. Now, plugging in rad 5 over 3, 2/3. Plugging that in, we get 23 over 27. And negative rad 5 over 3, 2/3. Plugging that in, we get 23 over 27. So these are the only possibilities where we could have a global max or min. Checking it out, we see where it is. The global max value is 1. It occurs at 3 different points. And the global min value is negative 1, and that only occurs once. Okay. And that's the answer to this question. Okay, so again, you can see that we're putting together all of our techniques. We're doing, part of the problem is to do a Lagrange multiplier calculation to find the critical points on the constraint. But in the end, and then the first step was to find local critical points. Once we have local critical points and boundary critical points, then we compare the function values of all of them in order to find our global max value and our global min value. Okay, so that was an introductory example. Now we're going to look at a harder example. So we're going to find global extreme points on the piece of a disk on one side of a line. So now notice that the boundary of this region is defined by 2 different formulas. So we're going to need to do those as separate cases. Now furthermore, the boundary has corners. And when a curve has corners, we know that the gradient at that point is not defined. So remember that when we think of derivatives not being defined, those give us critical points. So you could either think of these as boundary critical points because it's not defined, or I like to call them corner critical points. So here's the problem. Let's take a look. So let's find the global max-min for the function xy on the top part of the disk radius 2 centered at the origin, which is cut off at y equals 1. So just a quick little sketch to remind us what we're doing. So our region is that little region right there. Okay. So we're cutting it off at 1, even though the radius, it goes all the way up to 2. And it says the top part. Okay. So let's give this a go. So we have to find 3 different types of critical points. We need to find local critical points, boundary critical points, and corner critical points before we compare to see which ones, which is the global max and which is the global min. So let's check it out. So let's find those local critical points. So to do that, you take your partial derivatives, fx and fy. So for the function fx is just y and fy is just x, all of those must be equal to 0. So that just tells us immediately that the critical point here, the local critical point, is 0, 0. But now let's look on our diagram. 0, 0 on the graph is over here. Note that this is not on the region. So later on, when we look for our global max min on the region, we're not going to include this point. Okay, so let's keep going. Another easy one to sort out, the corner critical points. So where do the corner critical points occur? Where the circle intersects the line y equals 1. So the formula for the circle, x squared plus y squared equals, radius was 2, so it equals 4. And then we've also got y equals 1. So plug it in and solve. X squared plus 1 squared equals 4. X squared equals 3. X equals plus or minus rad 3. So that gives us 2 points. Rad 3, 1, and rad 3, negative 1. And those are the corner critical points. Now, we're going to take a look at the boundary critical points, and we know this is a longer calculation. So, boundary critical points. So we know that we need to find that there are 2 different pieces of the boundary. Each one has its own equation. We must do them separately. So, first case, we're using the formula for the circle part of the boundary, x squared plus y squared, and that equals 4. So notice that in this case, our function is x squared plus y squared, and equals 4, so it's a level curve of that function. And now we go to work. Grad f was yx, and now grad g equals 2x, 2y. And now we make our equations. Y equals c times 2x, and x equals c times 2y. So solving from the first equation, we know that solving, remember, the first thing we want to do is solve for c in order to eliminate it. So c equals y over 2x. And so now we plug that in to the second equation to get rid of c. X equals y over 2x times 2y. So solving that out, we get, with the 2's canceling, x squared equals y squared. If x squared equals y squared, then we can plug that into, notice that we can now plug this into the constraint equation, because the constraint equation just says x squared plus y squared equals 4. So now plugging that in, we get x squared plus x squared equals 4. Solving for x, x squared must be 2. So x equals plus minus rad 2. And since x is plus minus rad 2, x squared equals y squared, so we know from that that also gives us y equals plus or minus rad 2. And when x is positive rad 2, y can be either plus or minus rad 2. And when x is negative rad 2, again, y can be either plus or minus rad 2. It's a little unusual, but that's because we have the equation x squared equals y squared. Okay. So this gives us 4 boundary critical points. So that gave us rad 2, rad 2, rad 2, negative rad 2, negative rad 2, rad 2, negative rad 2, negative rad 2. Once again, we should refer back to our graph. Notice that we're interested in the top piece of the circle, and generally the top piece of the disk. So therefore, the ones with the negative y values are not on our region. The other ones with positive, positive, and then negative x but positive y, those are on the region. Those wind up being here and here, kind of like little Mickey Mouse ears. So those points we do want. Okay. Now remember, this was checking on the piece of the boundary that was the circle. We've got to go back and we've got to check on the part of the circle, the part of the boundary, which is y equals negative 1. So notice that in this case, you write it out, our function, we'll use g again, is just y, and that equals 1. So we already know grad f. In this case, grad g equals derivative with respect to x is just 0, derivative with respect to y is just 1. So now we make our Lagrange equations. So from grad f, again, we knew that was yx. So y equals c times 0, and x equals c times 1. So what does this tell us? So this tells us, from the first equation, that tells us that y equals 0. But remember that in this case, we were on the line where y equals 1. So therefore, this one is not on this boundary. Can't have both y equals 1 and y equals 0. Therefore, this doesn't give us any points. So now we have we've checked for local critical points. Scroll back a bit. Here we go. We've checked for local critical points, corner critical points, and boundary critical points. So altogether, the CP that we like are, well, 0, 0 was not on the region, so we throw it away. Corner critical points, we liked, or we can include rad 3, 1, rad 3, negative 1. And then the boundary critical points that are actually on our region, rad 2, and negative rad 2, rad 2. So again, it is important to check that the critical points that you turn up are on the actual region that you're interested in. So of all our critical points, these are the ones that are, and now we just plug them into our original function. And the original function was just x times y. So the function values for the first critical point, rad 3, second critical point, negative rad 3, third critical point, we get 2, fourth critical point, we get negative 2. And just by a quick comparison, there's our global max, the value 2, and there is our global min, the value is negative 2. We're going to look at one more case. So optimize this function, f equals x squared minus 2xy plus 2y. For this region, defined like this. X is between 0 and 3, and y is between 0 and 2. So again, a little sketch is going to help us understand how we're going to set this up. So notice that x is between 0 and 3, y is between 0 and 2. So that means that this is our region. So now if you think about what the boundary is, as when we get to the boundary part, the boundary is actually made up of kind of 4 separate lines. Each one is going to have its own equation. There's also going to be 4, the corner points, that's easy to figure out. There's 4 corner points. We'll talk about how to handle the boundary when we get there. First, let's start with the easier stuff, local critical points. So for local critical points, df dx, 2x minus 2y, and that must be 0. df dy, negative 2x plus 2, and that must be 0. So we can solve the first equation to see that x equals y. And solving in the second equation, very quickly we get x equals 1. And then obviously from the 2 equations together, also you have y equals 1. So put together, this gives us the critical point, 1, 1. And notice that that critical point is right there. Yes, it's on our region. Okay. Next, corner critical points. So those are pretty easy to identify once we recognize that our region is a rectangle. You get 0, 0, 0, 2, 3, 0, and 3, 2, the 4 corners of the rectangle. Now we find the boundary critical points. Okay, so if you look at the boundary, it's the perimeter of a rectangle. The best way to describe these with equations is 4 separate equations. So because we have 4 separate equations, we're going to have 4 cases. So the first case, let's use the boundary on the left side. On the left side, we have x equals 0. So that means that our function, g of xy, is just, x, and that equals 0. So let's work through it. I'm going to need more room. Okay. So gradient of g with respect to x is 1, with respect to y is 0. So now we make our equations. We previously calculated the gradient of f. We can pull it from over here because we have the partial derivatives. So 2x minus 2y equals c times 1, and negative 2x plus 2 equals c times 0. So solving the second equation gives you x equals 1. But notice that x equals 1, we're looking at the case where x equals 0. So it's not on this boundary. So we don't get any points, any boundary critical points from case A. Next. Case B. Is the boundary on the right, x equals 3. So our function g of xy is just x. And once again, the gradient of g is 1, 0. Well, we're going to set up the exact same equations to get the exact same result. 2x minus 2y equals c times 1, negative 2x plus 2 equals c times 0. Second equation gives us x equals 1, which is not on this boundary. Okay. Case C. Now let's take the bottom boundary. Y equals 0. So our function is y, and now we take the gradient. You get 0, 1. So that gives us the equations 2x minus 2y equals c times 0, and then minus 2x plus 2 equals c times 1. So the top equation gives us 2x minus 2y equals 0, therefore x equals y. But notice that we're in the case where y equals 0. So that tells us that x equals 0. And this gives us the boundary critical point 0, 0. Finally, case D, y equals 3. We'll get a similar calculation. Grad g equals 0, 1. So 2x minus 2y equals c times 0. Negative 2x plus 2 equals c times 1. First equation gives us x equals y. Therefore, now in this case, y was, on this piece of the boundary, y was 3. So this gives us that x equals 3. I'm sorry, this case was not y equals 3. I got it confused. This case was y equals 2. Sorry about that. Right. The top boundary is y equals 2. If you didn't catch the error, you may have caught the error before I did. Sorry. So these calculations are still the same, but now we have that since y equals 2 and x equals y, now we have that x equals 2. Okay, so this gives us the boundary critical point, 2, 2. And just checking our situation, 2, 2 sits right there, and yes, that is on our region. So now let's put it all together. I'm going to need to make a little room for myself. Okay, So now we will take critical points and plug them into the function. So we got local critical point, that was 1, 1. We got corner critical points, 0, 0, 0, 2, 3, 0, and 3, 2. And we got boundary critical point 0, 0, but we already have it. It was one of our corner critical points. And we also got boundary critical point 2, 2. Okay. So now we just plug each of these into the function and we see what we get. So 1, 1 plugged into the function gives us 1. 0, 0 plugged in gives us 0. 0, 2 plugged in gives us 4. 3, 0 plugged in gives us 9. 3, 2 plugged in gives us 1. And 2, 2 plugged in gives us 0. So a quick look at this tells us, that the global max value is 9 and the global minimum value equals 0. And we'll just note that the global min occurs at 2 different points. So we've optimized the function by finding both its global max and its global min. Notice that in order to do this, we had to find local critical points and corner critical points and boundary critical points, and then we just compare the function values. Okay, so those are all, that's basically everything we've learned about optimizing, all wrapped up in a single problem. And of course, we've done 3 examples of this. So let's just do a summary of everything that we know about optimization in all cases. So let's take a look. Okay, so first, we can find, for a function, we can find local critical points using the first derivative test. That just says that all partial derivatives, in this case df dx and df dy, must be 0 or dne. Okay. Now, if we have a local critical point, we can classify it with the second derivative test using the Hessian. And remember, the formula for the Hessian was fxx times fyy minus fxy squared. And remember that there's a 2-pronged part of the Hessian, of the second derivative test using the Hessian. So first of all, if the Hessian is negative, your critical point is a saddle point. It's not a max or a min. If the Hessian at your point is positive, then the critical point is an extreme point. But then we need to check what kind of extreme point it is. So if fxx at the point is positive, then the graph is concave up and the critical point is a local min. If xxx at the point is negative, then the graph is concave down and the critical point is a local max. And then if the Hessian is 0, we simply say that there's no conclusion. Okay. So that was the first bit if we're just thinking about local extrema. Next, if we're trying to find global extrema for a function on a boundary or constraint, if we have a function z equals f of xy, and the constraint we say g of xy equals k, then we find the boundary critical points, or the critical points on the constraint, using the Lagrange multiplier, which says that gradient of f equals some constant times the gradient of g. And we went through how to do that. And then, of course, you compare the function values at the critical points. Finally, we can put it all together by saying if we want to find the global extreme for a function on a region, then if for our function z equals f of xy, and our region has the boundary, which is the constraint g of xy equals k. First, we find our local critical points, then we find our boundary critical points, then we find our corner critical points. and then we compare the function values at all of the critical points. And our techniques involving the boundary, doing optimization on the boundary, this works for any number of variables.